Okay, great. All right. Hopefully everything's working. So anyway, welcome back. So today we'll continue talking about different quantum computing topics, and in particular, I want to talk a little bit about sort of going from algorithms to quantum circuits to give you the idea of the flow of how you go from algorithm to describe it by different gates and different operations inside the quantum computer. So as we kind of already discussed last time, quantum computers is a device that basically performs computation by manipulating qubits. So unlike classical bits, we have these qubits that can be in a superposition of different states, and then we leverage the quantum mechanical properties and like the Schrodinger's equation and the unitaries to describe how the system evolves, and that's how the computation is performed. So as we'll see, basically in quantum computing, that the whole goal is having you describe your problem as effectively an algorithm, and then you implement that on the quantum computer, and you apply the Hamiltonian transformation to go from the inputs to the desired solution. This is again just as a quick review, the diagram of a typical quantum computer. So in the quantum computer, we'll have the quantum chip or the qubits where you actually do the computation. Then you have a lot of the classical controllers that deal with sending the signals to trigger the different gates and read out the results. And then you have a lot of also classical infrastructure where you actually might, for example, read out the results from the circuit and optimize the parameters of the circuit and execute it again. So really, quantum computer is a small part of qubit and a huge part of a classical infrastructure around. And to kind of give some small connection to classical computers, in classical processor design and classical CPU, we talk about like a control path and a data path. So I think in quantum computers, the straightforward kind of mapping is that basically the quantum chip is sort of your data path. This is where the actual computation is performed. This is where you have all the qubits that are being manipulated by the instruction. So the quantum chip within the QPU would sort of be the data path of the processor of the QPU or the quantum processing unit, and then all the controller electronics would basically be the control path. So in a regular computer, everything's sort of inside the Intel or ARM or whatever Apple chip. Both the control path and then the data path is inside one chip, inside one package, and it's not really so separated. But in quantum computers, at least now, because of the huge size, the data path is really separate from the control path, and all the classical electronics deal with the controllers. All the qubits are in the fridge, for example, totally separated. But of course, in the future, hopefully, things are going to sort of converge. There's a lot of issues with if you have each of the qubits requires many control signals, many control lines. So if the controller and the qubits are separated, let's say the controller is outside of the fridge and the qubits are inside the fridge, there's a lot of overhead in terms of wiring and just kind of getting the thing to work. So in the future, the QPU might truly be a quantum processing unit, a single package. But for now, these are quite separate. And when we'll talk about running or executing quantum circuits, it's basically you go from describing an algorithm to describing a set of gate operations, which then the controller is responsible for actually issuing to the qubits to execute. And then another maybe short review from the previous time we met. So this is sort of the current sort of software stack of a quantum computer system. There's no operating system, no different kind of layers. You basically have the devices on the bottom that perform the computation, a little bit of software in the middle, and then the algorithm is actually what you want to run. So you really like a good analogy, I think, to classical computers is that it's sort of like running bare metal, that you directly executing your code on the qubits with really no abstraction layers. Once we have fault-tolerant quantum computers, there'll be sort of a more explicit abstraction layer, but until then we have really these three parts. And here here you have the algorithms are expressed as either we call them either quantum circuits or quantum programs. I think now now people more commonly just say quantum programs, but they basically mean quantum circuits. So whenever you have like a quantum algorithm, you have to transform it into a quantum circuit that you can run on the machine, and then there are some domain-specific languages for programming a quantum computer. So at the very end today, I'll just show one brief example of open QASM and Qiskit, but basically these are just like I don't know Python or C or assembly, just text-based ways of describing the circuit. And then one when we talk about I think programming quantum computer, we're not really going to talk much about compilation, but actually in quantum computing, one of the you know I think pretty large areas currently is really looking at a compilation. How do you actually go from the program that you write in some high-level language to the circuit that can execute on the quantum computer. And there are many challenges, mainly with the fact that, for example, the basis gates, which is basically the fundamental instructions that the quantum computer supports, might be different from what's written in the programming language. So, for example, like in classical computers, you have many operations available in Python, but the CPU only does multiplication, addition, but very basic operations. So, just like in classical computers, you have to compile from the program to the basic instructions or basic gates that the QPU supports. But also, there's a lot of other things that the compiler takes care of. For example, trying to add some noise mitigations into the circuit, or really dealing with the connectivity of the qubits, and just the sheer the number of qubits is so small that the compiler really has to work hard to try to optimize the circuit. So when we talk about quantum circuits and in general, I think in this course we're not going to really talk much about compilation, but I think it's one of the quite large areas in terms of, in order to get quantum computers to really work, you don't just need the hardware, you don't just need the algorithms, but you really need efficient tools to kind of make that connection. But this kind of maybe we skip that compilation part when we talk about the quantum circuits. So so now some maybe comparison between classical circuits and classical programs and quantum circuits. And I think that, of course, the fundamental thing is that in quantum computing, since you are using qubits, you can represent many more states using the available resources. So because of superposition, if you have n qubits, you can represent 2 to the n states, as opposed with classical circuits where you can just represent n states. So again, I just kind of keep repeating myself, but bits, we just have ones or zeros, and for qubits, we can have the superposition of those. And so that's one difference, is that you can have many more states available to you. Another, I think that was actually already mentioned earlier during the quiz. So classical circuits are in general not reversible. So gates like and or, you cannot kind of run them backwards. But for quantum computers, all the gates are reversible and can be sort of undone. And then I think one kind of important aspect, maybe a little bit overlooked sometimes, that quantum circuits don't really have things like if, else, other kind of conditional execution. Since everything has to be reversible, you will not really encounter like if statements in your code. It's sort of like you start in the beginning, and then you evolve your system to the end without sort of conditional things like that. So in a sense, it's sort of like just a straight line program that you can statically compile and execute from the beginning to the end. And then so in some sense, this makes quantum circuits on one hand a little bit easier. On the other hand, if your algorithm somehow has some conditional logic in it, you have to find a way to represent that, or create a circuit that you can represent it in this logic without if and else statements. So I think, again, transferring, in most of algorithms we think about have some conditional statements and loops and things like that, but that becomes much harder when you try to translate it into quantum computing domain. And now there's a little asterisk that there are really no if, else, and other statements like that. So it's kind of there are two things that sort of are in a way conditional. So one is this idea of a mid-circuit measurement. So maybe you remember from a previous figure, we have an initial state, we apply the quantum gates, and we go to the end, and then you measure them. And now since few years, a lot of the quantum computers also support this idea of mid-circuit measurement, which like the name implies, you're able to measure the qubits in the middle of a circuit. So as the circuit is executing, you can measure some subset of the qubits. The measurement gives you a classical 0 or 1. So you collapse the quantum state, you get a 0 or 1, and then you could use that as a conditional signal to execute another gate. So one example, for example, that uses mid-circuit measurement is, for example, active reset. So in an active reset mechanism, you take a qubit, you measure it. If you measure it into being in a 0 state, you do nothing. If you measure it and it ends up in 1 state, then you apply an X gate to flip it back to 0. So this allows you for like an if else type of operation. Now, one challenge is that if you perform the mid-circuit measurement, you lose the quantum state. So you lose sort of your quantum properties. So it sort of you have to be sort of, I guess, very careful how you design the mid-circuit measurement in terms of how you use it in your algorithm to actually really get some speed up from the quantum computation. Because if you just measure it, then you lose the quantum state. So I think some very specific cases where this has good utility is, for example, in error correction that we'll talk about at some point later, where you're measuring these these syndrome qubits to figure out if there was an error. And in this case, it's a positive use of mid-circuit measurement, but and it kind of allows you like an if then execution. The other it's not really an an if then state kind of a statement, but it does have like an if condition, and this is the CNOT gate. So we'll read about at the CNOT. We'll discuss about the CNOT gate. So CNOT is the control NOT gate, and basically, as the name implies, if based on the control on the control qubit, you either flip the target qubit or not. So it reads sort of like a if else, if one, if the control qubit is 0, then nothing happens. If the control qubit is 1, then the target qubit is flipped. So it sort of reads like a if else. But remember, because we're working on qubits, this actually gets interesting, because if the control qubit is in superposition, then after the operation is done, you both have applied and not applied the CNOT gate. So we'll use CNOT gates quite a bit in different circuits, and it's a reversible gate. It's just kind of, when you read the description, sort of sounds like an if-else statement, but it's not really. So I think that's a kind of one important thing to remember, that the circuits don't really have kind of conditional statements. And then so before jumping to talking about quantum circuits, just very basic review of Boolean circuits and then Boolean logic. So again, in classical computers, we work with just ones and zeros, and typically there are different ways. Just like in quantum computers, you have different ways of realizing the qubits. In classical computers, you have different ways of realizing the bits. So in DRAM, you either have charge or no charge. Or on disk drive, you have either the magnetic particles in the disk platter are magnetized one way or the other, or you have high or low voltage in circuits. So you're basically working with just two states, ones or zeros, and in classical circuits, again, very basic. Like you apply your inputs, then the inputs flow through all the different logical gates to achieve to come to the result, right? And then the gates are not reversible, and then as you execute, basically the higher low voltages trigger the transistors in all the gates, and then all the gates basically represent Boolean algebra operations that you apply to the inputs to achieve the output. And in this sense, it's a little different from quantum circuits, where in classical circuits, you define the gates, and then sort of the data or you can think of it as this sort of the data flows through the gates to achieve the computation. In quantum circuits, although we call them circuits, it's sort of um, the other way around, where the qubits are fixed, and then you're applying the gate operations to them. So it's a little bit different. But and again, in classical circuits, once you have some sort of basic circuit, you can build an adder, multiplier, and then things like that. And then on top of that, you can build an ALU and then a whole CPU, and you execute a program that basically triggers a bunch of computation on the underlying circuit. So in quantum computers, we're sort of more at this stage where all the programs are defined as a circuit, and then that's what you execute. It's not like in a CPU where you have a circuit and then your program runs on top of the circuit, on top of the transistors, but you're just directly executing the quantum gate. So again, I think the best analogy is like a bare metal execution, where you're just specifying the circuit and running it on the hardware. Okay, so again, just kind of going a little bit, kind of try to make a connection to the Schrodinger's equation and the unitaries, but keep this picture in mind now. So as we switch to quantum circuits, we no longer have this picture of inputs going through different gates to the output. Sort of, you can keep this kind of generic picture in mind, where now you have different qubits, and then sort of as the time progresses, you evolve. You have some initial quantum state, and then as the time progresses, you apply the different gate operations to evolve the state, and then you eventually end up at some final state. So as we'll see, that the purpose of sort of if you have a quantum algorithm, the whole the hard work is how do you define a circuit that takes some initial state and transfers it to the final state defined by the algorithm. So any quantum algorithm is basically a function that takes some input, quantum state, and goes to the output. And in most cases, when we okay, so yeah, so if there's some explicit initial state for the qubits, okay, you have some initial state, but in general, for all the quantum circuits, you'll start all the qubits are assumed to start in the ground state, in the zero state. So kind of like okay, not exactly true, but when you turn on your computer, let's say all the registers should be in zero state, all the memory should be zeroed out. So same for the quantum circuits. You start in a zero state, and then you evolve them through the different quantum gates. And then next few slides, I'll try to make a connection from the sort of the how you go from algorithm to kind of individual gates. And the key part is that basically and again, an algorithm is just a function that transfers some input to the desired output. And in a quantum algorithm, basically you can think of it that the whole algorithm can be defined as a huge unitary. So if it was possible, you could simply take your qubits in the initial state, define a huge unitary that describes the operation of your algorithm, apply that to the qubits, and you would arrive at the end result. So basically, if you have if you have this Hamiltonian, which describes how the system evolves, corresponding to your algorithm, you could define this one huge unitary, and you would be done. But in practice, this is not possible. You cannot have a quantum computer that could execute such a huge unitary. So the whole sort of, I guess, the whole work of going from an algorithm to quantum circuits is how do given some description and a huge unitary that might describe the algorithm, how do you break it down into individual operations that can actually execute on a quantum computer? And just as an aside, since we'll be talking a little bit about unitaries, so we saw that that we can define a qubit as this combination of the basis states, but you can also define a qubit as a column vector, or it's called a state vector. So basically, when you have the state vector, you're basically listing the vector contains the amplitudes associated with the different basis states. One qubit is described as a vector of two elements, and for example, a zero state is a 1-0 vector because the probability of the zero state is the square of the amplitude is the probability, and then so the probability of zero state is 100%, and the probability of one is zero. And then, for example, the one state is described by the state vector 0, 1, where the probability of the zero state is 0, and then the probability of the one is 100%. So you can use the vectors state vectors to describe the quantum states, and then basically the unitary is a matrix that sort of describes how you change the state of the qubit, and then so this is for one qubit. For a 2 qubit system, the state vector would have four entries. So in general, the vectors for an n qubit system, the vector has 2 to the n entries corresponding to that qubit, and we call it for a 2 qubit system, it's basically a tensor product of the individual cube. So we can describe the qubits basically as these state vectors, and then we can describe the gate operations as matrices that act onto the state vectors. So we'll come back to this matrix representation in a few slides, but just to demonstrate, so a unitary matrix can describe some operations such as this control NOT gate, and then in this case, a control NOT gate. Maybe you remember from the description earlier, there's like a control qubit and a target qubit. So a control NOT gate operates on two qubits, and then so for 2 qubits you need a state vector of four elements. So the matrix that describes the CNOT gate is a 4x4 matrix because it's operating on a 2 qubit state vector, and then this, for example, the representation of the CNOT gate, and then just one example, like I'll come back to this Bell state example, but a Bell state circuit is a very simple example that shows entanglement, and then in this part, this is sort of a second part of the Bell state computation. Once you have a qubit in a superposition, then you apply the CNOT gate to entangle it, and you have the final entangle result. But maybe for now, the main thing to just see and remember is that you have some state vector that represents the state of the qubits, and then you apply the unitary to go to the next state of the system. So all the gate operations can be these matrices. So if you have a 1 qubit operations, you have a 2x2 matrix. 2 qubit operation, you have 4x4 matrix, and if you wanted to coming back to this slide, if you want to have a unitary that describes the operation of a whole algorithm, then for 100 qubit algorithm, you'd have 2 to the 100 times 2 to the 100 matrix that describes that, which is not possible. So in the end, we'll try to decompose the circuits into these basic operations. But we'll see the for a lot of the quantum gates, you quite often see the matrix representation of the gates. Now how do we get from like a possibly huge unitary that describes the operation of the algorithm to individual ones? So this is actually one of the key challenges is how do you break this huge Hamiltonian or huge unitary into a smaller chunks, and this is actually called this part of the compilation, or sometimes called quantum synthesis. Is how do you go from a description of this large unitary to a smaller one? And there are many different algorithms, and a lot of them are sort of incorporated in existing compilers, so you maybe don't have to worry about the details. But basically the key is that you start with some huge Hamiltonian or a huge unitary, and you want to break it down into smaller parts. And one of the approaches is called trotterization, which is effectively changing. You change a huge. So the again the Hamiltonian describes how the system evolves over time, and then you can basically change that into a set of smaller steps that you sort of, instead of evolving whole system in one go from the beginning to the end, you just evolve it piece by piece, and then in the end, like that accumulates to be the same result. So with trotterization, you start with a huge Hamiltonian, and then you break it down into smaller parts, and then maybe you remember, this can a unitary can describe this evolution, and then if you break it down into smaller parts, each of these can be described by a new unitary as well, but actually, it also is also smaller than this one. So you end up having one huge unitary that is sort of instead of that, you use a sequence of smaller unitaries that are applied in sequence to the quantum states, and so that's how you get that picture of, you start with a quantum state, and then each unitary will become a gate. So you start with a quantum state, and you apply the gates in sequence, and then the end result is what you wanted. So this trotterization is one approach. If you have the Hamiltonian that describes your what you want to do, you can break it down into smaller unitaries, and then if you break it down small enough, you end up with just 1 or 2 qubit operations. So you end up with unitaries that are either one for 1 qubit or 2 qubits, which are very small. You can actually execute on the quantum computer. If you already have a unitary to begin with, instead of the Hamiltonian, then there are other techniques like matrix factorization, again, to decompose this huge unitary into smaller parts. But the key thing is, ideally, you would want to execute things at once in one go, but we can't, so we have to change it into smaller chunks. Any questions at this point? Okay, all right. Okay. Yeah. So again, going from the algorithm to the circuits. Again, every quantum gate corresponds to a small unitary, which is derived from this Hamiltonian. So in the end, so on one hand, you have your algorithm that you're breaking down into smaller chunks. On the other hand, the quantum computer supports a certain set of operations, each described by a unitary, and so kind of you want to put it together where the compiler, sometimes also called the transpiler, or compilation is called transpilation, is basically trying to fit a sequence of these small Hamiltonians that correspond to the basis gates of the quantum computer to the huge Hamiltonian that describes what you want to do. So that's kind of the dirty work that how do you go from a big Hamiltonian to these smaller steps that you can actually execute. And then so coming back to this picture, we have a quantum circuit, and then at the end, this is a quantum circuit, which is set of unitaries, and then so as the time progresses, you apply the unitaries to the quantum states to evolve the system. And I was boring this picture, so in practice, you only have either 1 or 2 qubit gates. You wouldn't really have these huge multi-qubit gates here shown on the right, but kind of the pattern holds that you evolve it through different steps. Yeah, and then finally at the end, once your circuit finishes, you have to do the measurement, and at least in the noisy machines, because there can be noise that accumulates to the computation, you want to execute it many times. So the same circuit from the beginning to the end would be executed many times. Each time, you start from the same state, you go through all the state evolutions to go to the result, and then you collect the output probabilities. So that's kind of how you go from, you have an algorithm, um, some Hamiltonian that describes it going to the individual gates. Um, and yeah, just as an aside, the compilation is really, I think, kind of very important and challenging part of quantum circuits. And then when you're doing the compilation, you want to break the circuit into individual instructions that can be executed. But for example, different methods like trotterization, they do introduce some errors. So you have to, maybe add some extra gates or sort of account for things that are introduced when you're simplifying the circuit. And then another important thing is that like for example, let's say in this picture, there's some qubit 1 and 2, and then you have this U2 operation that operates on the two qubits. So that assumes that you can perform a two qubit gate on these two qubits. And even though the quantum computer might have a two qubit gate, maybe actually the two qubits you want to connect are not 1 and 2, but let's say 1 and 10. So then, for example, the compiler has to know kind of the layout of the quantum chip to do what's called swap. So basically, swap around the quantum states so that you can actually basically execute the two qubit operation. So maybe you can think of it here, like if you wanted to do a two qubit gate between, let's say, qubit 1 and whatever qubit 10, before you can actually execute a gate, you have to bring them closer together so they can be executed. So this is sort of the limitation of the quantum computer, that although it can do two qubit gate operations, maybe it cannot do two qubit gate operations between every pair of the qubits. And then this is the topology. Also, this is or you can also get connectivity. So for some quantum computers, like superconducting qubits, only certain qubits are connected, so you cannot do sort of random two qubit gates between any pair of qubits without swaps. But for other like neutral atom architectures, you can have all-to-all connectivity. So different quantum computers. If I can skip back a little bit, they different quantum computers will have the different basis gates, so the different gates that they support. They will have different topology. So when you're breaking down when you're breaking down, when you're breaking down the circuit, you want to the unitaries that you can target can be specific to a machine for different types of gates, or also constrained by the topology. And then there are also other things like you can get fancy, and instead of using a set of predefined gates, you can use sort of maybe some custom gates with some pulse level control to define a new type of gate that might be useful for your algorithm. So that's kind of I think the compiler can try to do. Okay, all right. So next two slides, I thought I can just very briefly introduce some of the programming languages for quantum computers. We'll hopefully do a demo on one of the next meetings, but just to give you an idea of how it actually works in practice. So in general, just like with regular computers, we have sort of low-level sort of assembly-like languages and higher level languages. So for lower level languages, and these are just some example, almost every other company has their own language they're trying to promote. So there's many different variants, but at least for low-level languages, I think Open QASM or Open Quantum Assembly is sort of the kind of like the most common denominator, or the standard that's supported by a lot of tools and a lot of vendors. And just as the name implies, it's basically an assembly language where you can write the exact instructions that the quantum computer executes. And so that's raw instructions, just like you write assembly. And excuse me, there's a Quill for example, from Rigetti, which is a different superconducting machine. So again, many vendors have their different tools, but at the end of the day, for the low-level languages, it's literally, you're you're specifying, which gate goes after which gate and targets which qubits, and that's what the quantum computer executes. So if you're writing in open chasm or something similar, you already have to have the algorithm, then you had to, on pen and paper or on your computer, you had to transfer the algorithm into a set of the gates that you can execute, and then write the assembly language, right? So like you have to be your own compiler. But of course, a lot of people don't want to do that, and it's not efficient. So now there are many high-level languages. And again, um, every company has a different one that they're promoting, but Qiskit, for example, is one of the, sort of most popular again, from IBM. And it's sort of, and in Qiskit, yes, you can write individual quantum gates, but it provides, many functions, many pre-built libraries, many predefined functions. So it's really like, like a software. Qiskit is basically like a software development kit for quantum computers, where it's a compiler, a set of simulators, a set of libraries for known circuits. And well, I think one common thing, I think, I'm gonna lie, but besides Q Sharp from Microsoft, majority of these are based on Python. So basically, these are Python packages that you can use, which means that you can use, you can, in the same Python environment, you can have your quantum circuit, but you can also, whatever your classical, PyTorch or whatever you're using for other computations. So everything is really, basically everybody's just using Python to program quantum computers. And then like the Qiskit the SDK would have a compiler that can generate the open chasm assembly, for example, um, that executes on the quantum computer. Um, Okay, so how does it actually look? So it looks pretty much like assembly when you write down the circuit. So this is an example of a Bell state circuit where you're basically entangling two qubits, and I think the syntax is pretty self-explanatory. You have some include or some definitions at the very top. This is open a chasm 2.0. I believe there's 3.0 in development or either already published. And then for the actual quantum circuit, it starts by defining the quantum registers and then the classical registers. So QReg is your qubits, basically. So this circuit will have two qubits, qubit 0 and qubit 1. And then it has two classical registers, classical registers 0 and 1. So the idea is that your computation is performed on the qubits, but at the end you perform some measurement, and then the classical registers is where you're storing the result of measurement in from the circuit. And for different reasons, the number of classical registers does not have to equal to the number of quantum registers. Like, for example, if you have mid-circuit measurement, each time you measure the same qubit, you could be saving the results into a different classical register, for example. So quite often the quantum registers or qubits and the classical registers are equal, but they don't have to be, so they're specified separately. And then once you specify your qubits, this is basically the circuit. And it's sort of I think that a good analogy. I don't know how many of you done like Verilog or VHDL? Probably. Yeah. So I think that when you think about quantum circuits, it's probably better to think of them more like a Verilog this hardware description than a software description. Basically, you have a textual listing of all the operations that are supposed to be applied to the qubits. But if there's no dependency on subsequent instructions, even they're written on a separate line, they actually could be executed in parallel. So like again, like in Verilog, all the statements are, all the logic gets generated in parallel, and things which are in sequence, they don't have to be necessarily. So in this case, they're in sequence because this CX or C0 gate depends on the H gate, but let's say if you hit another gate, let's say H gate, qubit 3, then H gate on qubit 0 and 3 could be executed at the same time. So yeah, so think of it as sort of like Verilog basically. And yeah, you apply H or a Hadamard gate to qubit 0 to put the qubit 0 in superposition of 0 and 1 states, and then you apply a control CNOT gate or controlled X gate to the uh, uh, qubit 1, and then you perform the measurement, so you read out the two qubits. And so I think writing the actual code is not very difficult, of course. I think the challenge is like coming up with the code. Like how do I transfer an algorithm to a set of quantum gates? And once you have that, writing the thing becomes very, very, very easy. Uh, uh, um, yeah, any questions here? Uh-huh.
It's up to the compiler then to determine the dependencies, like the first gate and the second gate both operate on Q0, so there is a dependency.
Yes, yeah, right. So yeah, so although this is sort of like assembly, like yeah, the compiler still has to figure out it still gets compiled and it figures out the dependency. Also, how does this circuit is using two qubits, but like which physical two qubits on the quantum computer, that's up to the compiler. I mean, you could tell it, you could have like a specification, but if you don't tell it, the qubit 0 could be mapped to qubit 64, and qubit 1 could be mapped to qubit 65. So like how it map, and then right. So how you map these qubits from your program to physical qubits is the compiler's job, and then there's a lot of optimization because different ways you map it, that might mean certain qubits, are closer and farther than each other. So here, like when we talked about um, uh, the swap gates, so when we talked about the swap gates, for example, uh, yeah, the topology, right? So the different placement of the qubits would maybe result with different number of swap gates that need to be inserted. So yeah, place and route of this is very important. Uh, and then and if for some reason, so all the quantum computers will support a set of a single qubit gates and at least one type of a two qubit gate. But if for some reason the target computer supports gates that are not in the program, then you also have to do another path where you transfer this program to the set of gates that are supported by the quantum computer. So there's still some compilation that goes on. Question, yeah. Uh, yeah, yes, in a way, yes. So the compiler, yeah. So first of all, from the program, it figures out what things can be done in parallel or not based on the control flow. But for example, if you target a machine, let's say like a trapped ion machine. So in a trapped ion machine, there's a limited number of traps, which are basically where you can execute the CX gate. So let's say if your program, you can execute, I don't know, 100 CX gates together because they have no dependencies, but maybe the hardware has some limitation that you can only do 5 at a time. So yeah, so you can think of it that yeah, like the quantum assembly is like your assembly, and then you have like an Intel compiler or an ARM compiler that translates that really to the actual machine. But yeah, figuring out that, yeah, what can be done in parallel based on the program, what can be done in parallel based on the circuit, how to assign the qubits. These are all things that the compiler has to do.
So how does the scheduling of the actual gate operations work? Like, what if I have like a qubit that's just sitting on the side and I have 5 other ones that are all running a circuit together? So will it just do, if I'm done using some sub qubits, will it just do all the measurements right away? Or it's going to wait until the very end?
Good question. So I guess it would depend on the functionality of the qubit. So in general, all the qubits are sort of measured at the end because you need all the qubits for the computation. But if some qubit the computation finishes early, then you could measure it then as well. I think there's an interesting case that, let's say there's a qubit that's idle other qubits are busy, this has to be idle, and then at some point it's used again. So sort of the qubit might be sitting idle for a while before it's used because other things are working in parallel. So in classical computers, this is not a problem because the register just sits there. But in quantum computers, it will start decaying. So for example, the compiler might notice that a certain qubit is idling for a long time, and it would do some error mitigation to kind of reduce the noise while the qubit is idling. So figuring out, can you do the measurement early or not, or if the qubit is really idle, how do I, mitigate the errors on that qubit while it's waiting? That's all the job of the compiler. But at the end, everything is sort of, statically compiled. You figure out which pulse or which gate to fire at what time on the target machine. Really good questions.
So, like send the circuit to some machine across the internet. I'm sending this, or this is compiled, and then I'm sending.
Yeah. So how you submit circuits sort of depends on the tools you use and on the service. So for example, a lot of in general, this has to be compiled to the target machine. With tools like Qiskit, you can compile it on your own machine and then submit the compiled circuit to the machine. Or some vendors, they basically provide you like a cloud environment where you program in a Python notebook on their server and then compilation gets done there. So in general, you can either, it really depends. Either you just like I can compile a binary and submit to Amazon, or I can compile it on Amazon's virtual machine and then run it.
I guess more generally, I'm asking like, is this the lowest level machine independent representation?
Yeah, I think so. Yes. So you can have like a pulse level control, which would be like really control the amplitude and the phase of the different control signals, but that's very specific to each machine. So I think that the goal, like regular assembly, that quantum assembly is sort of the least common denominator for many machines, and then from that you go um, uh, you target each specific hardware. Okay, really cool. So so hopefully one of the next meetings we'll actually try to do some of this programming. But the other higher level representation is Qiskit, and this example doesn't do justice to all the things that Qiskit can do, but just to compare to the assembly. So if you wanted to do the same Bell state circuit, so Qiskit is basically a Python program. There's a Qiskit package that you can import in Python, which creates this quantum circuit object. And if you wanted to create the Bell state circuit, you initialize a quantum circuit object with two qubits and two classical registers. So you initialize it, and then the syntax is a little bit different, but it's the same idea. You take your quantum circuit, and then you apply the H gate to qubit 0, and then you take your quantum circuit, and then you apply the C0 gate to qubit 0 and 1, and sort of again you progress this way. And Qiskit and other SDKs have a lot of functions that you can generate some specific circuits or has some optimization. There's a lot of features, but if you want to translate the assembly to Qiskit or Qiskit to assembly, this is kind of, I think, the most equivalent, that you define your quantum circuit, you specify the quantum gates, and then you do you measure the qubit 0 and 1 into classical registers 0 and 1. So again, the number of the classical registers and the order could be different, and but this is in Python. So I think most people just write in Python and import one of the packages, and then you can and then there are many different features for plotting and things like that. So it's pretty convenient. But again, the challenge is not this part. The challenge is figuring out what's the sequence of the gates that actually implement your algorithm. That, like, once you know the sequence of the gates to implement your algorithm, actually writing it and executing is not a problem. Okay. So only a few more slides. So now I just wanted to maybe jump very very briefly to just show what type of gates are commonly supported by the different by the different quantum computers. So at the end of the day, we have these different H gates or CX gates. They're sort of fundamental gates that you can execute on the quantum computer, and each of them corresponds to some unitary that evolves the states of the qubits. And here's some common gates, and also you'll start to sort of pattern match the different diagrams of the gate. So for example, X gate or a NOT gate, it basically flips the qubit. So if you apply a NOT gate, it's a single qubit gate to a qubit, then if it's in a 0 state, then it goes to 1. If it's 1, if it to 0, so basically flips the state of the qubit. And if you have a CNOT gate or the control NOT gate or also called CX gate, now you have two qubits. You have a control qubit and a target qubit, and then you can see that if the control qubit is 0, then the target is unchanged, and then if the control is 1, then the target is flipped. So it's a controlled flip, but this is for sort of qubits in either 0 or 1 state. If the qubits are sort of in superposition, then you end up with superposition when you apply this. But as you can see, again, all the gates are reversible because for all the outputs, there's only one input that corresponds to it. So you can always reverse the gate. And a toughly or controlled NOT gate has two control inputs, and then this is the target. So in this case, if only if both controls are 1, then you flip the target. So this basically lets you change the state of the qubit. And then Toffoli gate has one interesting application that you can kind of use it to simulate classical Boolean logic. So for example, if your quantum algorithm requires a quantum adder, then inside the quantum adder, for example, you might be using a Toffoli gate to implement basic logic that implements a quantum adder. So it's quite useful. But if the hardware doesn't support the Toffoli gate, which is a 3-qubit gate, then that gate has to be decomposed into smaller 2-qubit gates, for example. So this can be used to simulate classical gates. And here are some more of the common gates. So we have and this also shows the matrix form for reference. So you can see how if you apply it to the state vector, how it would change the state of the qubit. So you have identity, which identity basically keeps the state of the qubit. So 0 goes to 0, 1 goes to 1. This NOT gate or X gate basically flips the state of the qubit from 1 to a 0 and 0 to a 1. The Z gate flips the phase, so the qubits also have phase, and then so this goes from positive to negative or back, and then the Y gate is sort of combination of the X and Z gates, and there is so here if you remember the block sphere, for example the X gate is sort of like rotating 180 degrees on the block sphere. Now you also have things like an S gate, which basically rotates by 90 degrees around the sphere, or things like a T gate that rotates by 45 degrees around the block sphere. And we already saw earlier in the examples, the H gate or the Hadamard gate, which basically puts the qubit into superposition of the two states. So to achieve useful quantum computation, basically you need a subset of these gates, and then you also need some sort of a 2-qubit gate. So pretty popular is the CNOT gate, but you can have a CZ gate, which works on the phase. So you just need some sort of a 2-qubit gate or a 3-qubit gate to really achieve entanglement. And again, they're all reversible, and this is the sort of the matrix representations that for these gates. So when you use different machines, they might support different set of basis gates, but they will likely come from these gates. And then so coming back to the sort of the algorithm, how to say it? So on one hand you have an algorithm that you're breaking down into smaller gates to match the unitaries of the gates supported by the quantum computer. But on the other hand, people are designing the quantum computers. So if somebody finds out that there's a certain gate that they can implement more efficiently or with lower error rate, then the different quantum computers could support different sets of gates. So that's sort of like some differentiation between the quantum computers is like which machine support which set of gates and how good they are. It's not like everybody has to support CNOT gate. They might support another 2-qubit gate if it's somehow more efficient on that architecture. So on one hand you have sort of software people breaking down a circuit into like a compiler, compiling into small instructions. On the other hand, you have sort of more hardware people proposing new types of gates and instructions, and they sort of we end up with this like software hardware co-design where it's not purely new compiler or purely new hardware will not help you. You have to have kind of both. You have to compile things efficiently, but if you come up with new type of a qubit that has really efficient but weird gates, maybe that's good. Maybe so the set of basis gates might change. Okay. All right. So I just have actually maybe only two or more, 2 or 3 more slides, but very briefly just want to talk about just interference and then entanglement. So these are probably the main features of the quantum computer, and I think like interference is really the key part. Like if your algorithm doesn't exhibit any interference, you're probably not really using any quantum properties, and you're not getting any quantum advantage. So really you have to have interference to sort of certain states to cancel out with each other to drive you to the solution. It's not mentioned in the slides, but there's actually another thing that's related to interference is amplitude amplification. So you try to interfere and cancel out amplitudes of the states that don't correspond to your solution, and at the same time you try to amplify the state that corresponds to your solution. So the whole goal of a quantum circuit that has some advantage is to have a bunch of inputs and then sort of interfere the states and amplify certain states to go to the solution. And how you do that is the magic of algorithm design. And if you're really good at it, let me know. I think it's a really huge challenge. How you actually design the algorithms and find some things. But for the interference, the main thing is that the qubit the qubits are basically described by the different amplitudes of the basis states, and these can basically interfere with each other. So you can actually constructively or destructively interfere to kind of cancel out some states. And this is just one example of interference with a set of Hadamard gates. So we already saw this H gate here, this Hadamard gate, which basically puts the qubit into superposition of 1 and 0. So you end up with if you apply H gate to a qubit in a 0 state, you end up with a qubit that's 50% in 0 state and 50% in 1 state. So and then this is the matrix representation of the H gate. So when you apply to the if you take the qubit in the 0 state, and then you apply the H gate to it, you end up with this where you have 1 over square root of 0 plus 1 over square root of 1. And then if you square this, you get half a chance, 50% chance of 0 and 50% chance of 1. And then so if you apply one gate, you get into superposition. But we can see the interference when you actually so if you apply Hadamard gate actually again, you end up with the original state, and this is sort of one example of interference. So so in a circuit, if you start at zero state, you apply two H gates, you would end up back to the zero state, and then so the idea is that after you apply the H gate one time, you can apply the H gate the second time, and then if you multiply things out, you see that after two applications of H gate, the amplitudes of zero end up adding up, so the probability of zero becomes one, and then here the amplitudes associated with the one end up canceling out, and it becomes zero. So this is sort of one example of interference where the amplitudes corresponding to the ground state add up, and then the amplitudes corresponding to the one state interfere, and then the one state goes away, and you end up with just as a zero. So just a simple example but this is how interference works. And then the trick is, for a huge algorithm, you have hundreds of qubits that describe your state, and you just want to amplify one of those states. And then and entanglement. So this is also actually related to the Hadamard gate. So when you entangle two qubits, you effectively put them in a state that they're correlated. So either they're both 0, 0 or both 1, 1. So to create entanglement, this is a most basic circuit where it's called a Bell state circuit. So you start with two qubits that are in the 0 state. You apply Hadamard gate to one of them to put that qubit into the superposition, and then you apply a CNOT gate. And maybe you remember I mentioned earlier, when you apply the CNOT gate based on the 1 or a 0 of the control, it flips the target. But now the control is actually in superposition of 1 and a 0. So you end up with this entangled state where you have 1 over square root of 2, 0, 0 plus 1 over square root of 2, 1, 1. And then so the weird entanglement phenomenon ends up that if you have a qubit in this state, when you measure it, you have 50% of chance of being 0, 0 and 50% chance of being 1, 1. And there's no chance of being any other state. So this when you measure this will never be in 1, 0 or 0, 1, which basically means that the qubits are entangled and they're always either both 0 or both 1, and there's no way of getting the other state, which is really cool. And then if you change, these are photons, let's say, and you send one photon somewhere very, very far away, they remain entangled and always kind of correlated. So yeah, so just an example of using some gates to, in this case, to get the entanglement. Okay, so just to wrap up, maybe just some again, talking about some constraints. So I think I already passively mentioned it, but for the NISQ machines, at least, you execute each circuit many times, hundreds to thousands of times, to really collect the output probability. So when you execute this circuit, each time that let's say the H gate and the CNOT gate, they have some noise and some error. So to really observe these output probabilities, you have to measure many times to see that it's 50% 0, 0, 50% 1, 1. And then if you do it on a real quantum computer, you actually end up, you will see, let's say, 1, 0 or 0, 1, because the gates are not perfect, and then you didn't achieve perfect entanglement. So there's a lot of, you have to, this idea of shots. So it's like on a regular computer, you run a program once and it's done. But on a quantum computer, you have to run it many times, and then that's it. Once you have fault-tolerant quantum computers, that issue will go away. But for now, you have to, so you have to sort of, whatever the execution time of your quantum circuit is, you have to throw in a factor of, let's say, 1,000 because you have to repeat it many times. And yeah, I think I already mentioned that there's some this amplitude amplification also. You want to in your circuits, you include some known methods to amplify certain amplitudes, or maybe I mentioned earlier, you insert some error mitigation to deal with the noise. So there's a lot of a lot of moving parts to getting things to run on quantum computers. And then this is a kind of a, I don't know, a mix of mix of things, but just to kind of, again, just to mention again, so you cannot copy qubits. So that's one of the main challenges or benefits in some way of quantum computers, that basically you cannot copy qubits. And then, you need to have some qubit-qubit interaction to entangle the qubits to really get the benefit of quantum computation. But then once they're entangled, you have to have interference. And then there's a bunch of noise. Actually, when we start talking about the security aspects, a lot of the research has sort of exploited this forms of noise, like, gate errors when you execute the gates, or the readout errors, or decoherence. So these are all problems with the qubits. And, even though, on paper, this Bell state circuit should just execute two gates and give you an entangled pair, all this noise actually creates problems. And, if you have problems with a two gate circuit, you can imagine there are a lot of problems with like huge circuits. So I a lot of work has to go onto fixing these errors, but also it's a way for security attackers to kind of exploit them and until they're sort of mitigated. Okay, so as a wrap up, so hopefully talked about some of the quantum computing topics some more, and we'll try to maybe do a little demo of running some circuits, but then we'll switch more back to security and look at classical computer security issues and then how they translate to quantum computers. Okay, let me stop.